Okay, with the calorimeter, you notice that I constrained your design to involve a paper cup, a candle, and capturing energy through water. And I have to say that it was a design constraint. You probably wouldn't really design a calorimeter like this, but I asked you for the energy in, the energy out, and the efficiency, and I didn't explain this very well. Probably a better way would have been the energy input and then the energy captured in your calorimeter. So you know that this energy captured is essentially the energy that shows up inside the water. So this energy captured is the energy in the water. The energy input is the energy from the candle. I think you know now that the candle is producing, it's acting as a fuel. Essentially, the liquid is being combusted into combustion products that are all volatile. So what is the candle made of? You probably know, well, it's not a metal, it's not a composite, it's a polymer, and it's essentially a carbon-based polymer. It's essentially a petroleum product. So when you combust the candle, what you're doing is you're combining oxygen with a hydrocarbon, and you're basically producing CO2 and water vapor. So this has a heat value as a fuel. Now, some of you looked up the high or low heat value as a fuel, and got essentially an output of kilograms, a certain amount of kilojoules, not kilograms, kilojoules per gram. So however many grams of wax you use, paraffin, you produce a certain number of kilojoules as you burn it. Now, others of you had took the stance of looking up an average energy output per candle wax per second. So when you looked at the number of seconds that this was burning. Either way, it's a fine way of doing it. So whether you went this heat value route or the other route, you had to compute the energy input right here. And then the energy output was basically the energy that was captured here in the change of temperature. So what energies were involved? And I asked you to look at kinetic energy, potential energy, internal enthalpy, and G. Actually, you didn't have to look at these two because they're not really involved. Gravitational potential energy, obviously nothing is changing in its height, so this is not really relevant. Kinetic energy, again, it's not moving. This is the gross movement. But these other terms, internal enthalpy and Gibbs free energy, do show up inside here. So what I'm wanting to do is distinguish between these three energies. So the internal energy is really the energy, this is stored in the atom vibrations, also known as phonons. So mechanical vibration of the atoms, phonons. This is, what do I want to say? This is also called chemical potential, and this is the energy that is stored in the chemical bonds. This is different than the vibrations, that it's actually stored in these covalent bonds or whatever bonds that you have in the material. And the difference between this guy and this guy, or this guy and this guy, is this accounts for the changes in entropy caused by a chemical reaction. So what we have is that G equals H minus TS. And H is what H accounts for that U doesn't account for, is the work that a gas would do when it was heating up. So liquid heats up, it doesn't really change volume, but if this were a gas, it would change volume, and not only would you have changes in internal energy, you would be producing work here. So this accounts for both of the two happening. So where do we have what? Well, this is obviously you have gives free energy because it's a chemical reaction. You could also say enthalpy is, we'll say gives free energy, change of enthalpy here. You might say that because you've melted this, converted from a solid to a liquid, you might call this a change of enthalpy. You could equally call it a change of internal energy. And then up here, you know that you have delta U, or you might also say delta H, in terms of the changing energy content of the water.